So here we are going to take our RANKINE three-dimensional model and break it down to 2D. So the two-dimensional model, if you remember, the flow past the half RANKINE model, right? If this is the flow that's coming in this direction, and the flow is uniform, velocity, let's say be infinite, and you had the source here. Now you got the source. Okay, and that source, and you have a flow coming here, you will see that you generate a half a Rankine half a body, something like this. So your stream function will be psi of the flow plus the source. Remember, just we keep adding what we need. So here I need this and I need the source because this is what I have. So, and then I apply this to my problem, right, from our previous class. And then for angle of attack at 0 degree, assuming that it's completely horizontal, the angle of attack is 0. If this is 0, then your total stream function is equal to this. Okay, this is only, again, just remember, your y is equal to r sine of theta. Okay, this is where this comes from. And also remember that your x is equal to r cosine of theta. And you can show that y over x is equal to theta. Tangent inverse of this will give you this. Okay, so if you wanted the angle, this is how you'll find the angle. If you had your x and y. Okay, so got those ideas fixed. Inverse. Okay, so now remember what we want. We want to know the stagnation point, the radius here, the radius of infinite. So we do the same as before. We find your velocity, okay, using your your cylindrical coordinate system, and this is the expression that you get. V infinite cosine theta plus q, the source flow, divided by 2 pi r, and u of theta will be minus v infinite times sine of theta. So this is what it's going to look like. You got the angle theta here, you got the source flowing here. This goes to infinite in this direction. By infinite, I mean this is just keeps on going. It's a straight line, if you would. And then this keeps on going something like this. This is what it ends up being. So we want to find the stagnation point. Stagnation point is a location where these two are 0. So if I take u theta and I set this to 0, I find the stagnation point can be pi. So I evaluate pi in the first equation for ur, and I solve for r. And you find your r for the r location for stagnation point is q over 2 pi v infinite. Again, we are doing the same thing that we have been doing, right? Finding stagnation point, making ur and u theta equal to 0. So as we move on, your stream function then will be v infinite r sine of theta plus q over 2 pi times theta. And so if I want to know the value of my stream function along this path line, right? Along this line here, that would be, it gives me pi q over 2, because when I put pi there, this goes to 0, and this gives you pi. Pi cancels out, you get q over 2. So what he's saying is, actually, that will be q sub 0, and is valid all over the body. Okay, that's the value of, this is the value, the stream function has that value all over the whole surface of my half Rankine body. Okay, so I can solve for r to get the shape of my body by saying this is equal to q r, and I can solve for this. Another way to do this problem is you could have also, instead of solving for this, solve for y. Okay, I just like to work in polar coordinates, so it's easy for me to do this. Okay, so now that we have that, we want to find your RT. Remember, your RT is this value right here at the top, and at the bottom will be the same. So that distance is found by taking pi over 2, and we will derive this equation, so put pi over 2 there, and you find the value is q divided by 4, a q divided 4 times v infinite. Okay? So your problem basically, this is the location of your stagnation point from your source, q over 2 pi v infinite, and this is RT, q over 4 v infinite. And what you can show is as you go to infinity, this becomes basically q 2 divided by q divided by 2 times v infinite. And that happens when theta is equal to 0 and the streamline keeps on going to infinity. Okay, so with that said, what you find here is that another thing that you can also realize as I go in the infinite, right, is actually the full volumetric flow becomes Q, which kind of makes sense, right? So as I'm going over my body and I'm going to multiply whatever happens there times the same stream, it should cancel out. Okay, so this is the first part. The second part of this discussion is the flow past the full Rankine body, or what we call the Rankine oval. Okay, so this is the case when you had, if you remember for the three-dimensional model, you had the source and you had the sink, right? Where this is the sink and this is the source where everything is going out. They have equal strength. You got a stream velocity. And one thing I'm interested in, interested in two things. I would like to know what is the length of this body, and I would like to know what is the pressure along this body. So that's one thing we will find. And the other thing, just to know, this B is given. Okay, the distance where this is located, so B is given. That distance is completely given in the problem. So it's very interesting. You can actually see this in simulations. If you put this source in your sink and you have a uniform flow, you will generate an oval like this, which is kind of pretty neat. So now we got three things, right? We got the flow, we got the source, and we got the sink. So then expect that you're going to have the stream of the flow, we're going to have the source, and we have the sink. So if we just go and these were combined, if you go back to your previous lecture, taking the values and replacing them in here and not taking for alpha equal to 0. So your stream function will be v infinite r sine of theta minus q divided by 2 pi times the difference of the angles. Okay? Remember, this sign is because the source is ahead of the sink. Otherwise, it will be plus. Okay, so just keep in mind that your angle theta B can be written as follows. Angle using geometry, you can show this. Don't want to spend too much time on geometry here. And this source is located at minus B. This sink is located at B, and you can see it from here. This is the location of X and Y. So this is minus B, and this will be plus B. Okay, so your total stream function now in terms of y and x is given as follows. I have a purpose for which I translated all this in this form. There has to be a tangent inverse here. They're same, because we are adding this plus this. So this is a very neat feature of trigonometry. If you have tangent inverse of an angle, subtract the tangent inverse of another angle beta, that's going to equal to this. Okay, this is a very neat property, and we will be using it. So we move on, and so your stream function then becomes this. Okay, So if you want to find your velocity, you take the derivative of whole thing, this whole thing, and you get this. You want to find your v, you take the derivative of this and you find this. Okay. So I want the stagnation point. Stagnation point is setting this equal to 0. Okay. And you can see that this is going to be a stagnation point will be when y is 0, x is equal to L, which is what we are really looking for, right? So we can come in here. Let's keep it x for now and simplify this. You can see that v is automatically satisfied because when I put y 0 there, this whole term goes away, right? So this term is satisfied. And do a little bit of algebra here, and you find that this nice expression. And from this expression, let's go to next page. You can take this expression, and now you can bring this on the side and do a little bit of arrangement, mathematical arrangement, and you find that this is equal to 0. So the only way this can be 0 if the top is 0, and that's a quadratic equation. So as you can see here, then you go ahead and you solve for x, and you can see that by solving the x, this is the value. So this is x equal to minus L and x equal to L, where your L, the distance I was looking for, then was equal to this. Okay. Just note that in your problem, when we started everything, this is L and this is L, so total distance is 2 times L. Okay, so it's 2 times L. So this is the distance that you're looking for, L. And some neat things that we could do here. We want to find the pressure, but before we find the pressure, let me just show you. Actually, let's go and find the pressure first. So the pressure is given by using the Bernoulli's equation. And we derive this in class. And remember, your V is going to be nothing else than the square root of U squared plus V squared. And if I replace all this big expression here, take all this expression, I plug it inside there, you're going to find that you get this big mess here. You can pause the video if you want to write this, but not necessary because you can do it manually once you have the numbers and everything. But this is a kind of nice expression. And then if you wanted to find the drag, you just have to integrate the whole thing, respect to r and theta. So now the neat things that we can think, there are a couple of L over B, and this H, H is this distance right here. Okay, it's the distance from here to here. This is H. Okay, this is what I'm going to call H. Okay, so having that distance, we can come up with this nice L over B expression. This is all non-dimensional expressions, as you can see, and this is a non-dimensional quantity. You can do, you can see that the units here are L squared over T. Here the units are L over T. The units here are L. So you're basically, this is whole thing if you cancel, guess 1. So there, this is a dimensionless quantity. So, but it's really interesting to see this behavior of what happens to all this put together as this increases or decreases. One neat feature is when this actually, so when this value right here starts to increase in this direction, look what happens, right? In this direction, we are decreasing, okay? This is decrease. And this direction, we are increasing. As I'm decreasing, this value, you can see it becomes basically like a flat panel, right? That's what it becomes. It becomes flat. But as I start increasing it, I keep increasing it until it actually becomes a perfect circle. Okay, this is a circle of radius r. It's a perfect circle. So that has kind of nice nice features to understand what happens to a closed body Rankine model, because that means that by using the source and the sink, I'm able to create a perfect circle as well. That's great to understand the flow around the cylinder. That's going to be our next topic of discussion. And that's why it was important to actually understand the flow around the Rankine body.